Hey guys, this is Jay. Let's start off with a reminder that worksheets are posted Monday, Wednesday, and videos are posted Tuesday, Thursday. The essay office hours are attached in the description. The constants we'll be covering are all proton NMR related. We got integration values, upfield, downfield, how chemical shifts are affected in aromatic rings, and coupling, or peak splitting. The integration values in NMR are derived from area under the curve of each signal, and they reflect the number of hydrogens contributing to each of these signals. Thus, using integration values, we can make an educated guess of how many hydrogens there are coming from each of these signals. Let's take this NMR from Dr. Castleman's lecture, for example. We can start by dividing all of these integration values by the lowest number, which is 27. We will get approximate numbers of 1 to 1.5 to 1 to 1.5. Since there can be 1.5 hydrogens in the structure, we can multiply all of these numbers by 2 for the purpose of getting whole numbers, making the numbers 2, 2, 3, 2, 2, 2, 3. It is likely that the first signal from the left is contributed by 2 hydrogens. The second signal is contributed by 3 hydrogens, and so on. The ratios we get from integration values don't necessarily equate to the number of hydrogens. They're just ratios of the number of hydrogens contributing to each signal. Let's take this molecule for example. Recall that the number of signals from proton NMR equates to the number of chemically unique hydrogens. Thus, the hydrogens in blue box will generate one signal, and the hydrogens in red box will generate another signal. The ratio of their integration values is likely 1 to 3. But there are 2 hydrogens in the blue box and 6 hydrogens in the red box. So their integration values display a ratio, but not the exact number of hydrogens. Let's briefly review upon upfield and downfield. So a hydrogen that is more downfield is more deshielded. It has a higher chemical shift. A hydrogen that is more upfield is more shielded. It has a lower chemical shift. When a nearby electronegative group pulls away electron density, the proton has less electron to shield itself. The proton feels more of the applied magnetic field, thus giving it a higher chemical shift. So this is a chart that Dr. Castleman showed, and we can see that the aldehyde H and the carboxylic acid hydrogen are rather downfield. That's because they're next to an electronegative group. So we'll start by introducing some terms. In relative to the carbon with the methyl, 1 carbon away is called ortho, 2 carbon away is called meta, 3 carbon away is called para. These terms only apply for aromatic rings. And we'll go back to them again when we get into aromatics, but it's just nice to introduce them. EDG, electron donating group. It donates electron density into the ring, for instance, OCH3. EWG, electron withdrawing group. It withdraws electron density from the ring, for instance, NO2. If the aromatic ring has an EDG, the hydrogens will be more shielded, or more upfield. If the aromatic ring has an electron withdrawing group, the hydrogens will be less shielded, or more downfield. This effect is generally more notable in ortho and para positions, because that's where the charge is. So let's take a look at the resonance structures on the aromatic ring with this OCH3, which is the EDG. The negative charges are on ortho and para positions. So that's why this effect is more notable in ortho and para position, because negative charge means more electron density, means more shielding. Similarly, the positive charge in the aromatic ring with EWG are on ortho and para positions. But EWG is pulling electron density away, so these charged spots are less shielded. And there are exceptions to this rule. So we get to proton NMR coupling, or peak splitting. Coupling occurs in NMR because the proton nucleus can sense magnetic field of nearby nuclei through the nearby electrons participating in bonds. And these nuclei can affect each other. This coupling causes the splitting of signals into peaks. So we introduce two rules, the n+1 rule and the 3-bond rule. The n+1 rule says the number of peaks is dependent on the number of neighboring chemically equivalent hydrogens. It equates to the number of neighboring chemically equivalent hydrogens plus 1. The 3-bond rule. Hydrogens can only couple when they're within the distance of 3 bonds. That's because if they're too far, then they can't sense each other. And there are exceptions to this as well. Let's do a practice problem. For these hydrogens in boxes, what kind of splittings would we expect? Okay, so the hydrogens in the red box have 2 neighboring chemically equivalent hydrogens, so the purple ones. The blue ones are too far away because they're more than 3 bonds away. So 1, 2, 3. 3 bond only gets us here. The hydrogens in purple have 3 neighboring hydrogens, so by n+1 rule, it is a quartet. The hydrogens in blue have 0 neighboring chemically equivalent hydrogen, as they're too far away, so by n+1 rule, it is a singlet. And on the side, there are some names corresponding to the number of peaks. So a question to close out the video. This hydrogen is particularly interesting because it's neighboring 1 hydrogen on the left and 1 hydrogen on the right. But these 2 hydrogens are not chemically equivalent. What kind of peaks would I get? It has to do with complicated splitting. So thank you guys for watching. If you guys have any questions or suggestions, you guys can comment in the session, email me, or ask me during my office hours. Thank you again.